the new stuff is easier than the series stuff, which isn't saying a lot. But the new stuff is kind of, it's more fun. You know, hello. It's not nearly as abstract. It is stuff that you will definitely see going forward, so it's important. But it's much more, it's easier to conceptualize what's happening with the new stuff. The old stuff, the infinite series stuff is, you know, very abstract, difficult to conceptualize for some people. So let me ask you this. We're in 2 dimensions mostly. If you go into 3 dimensions, we need to be able to graph objects in 3 dimensions. The simplest object that we could graph is a line. Somebody tell me what the equation of a line is first in 2 dimensions. What's the equation of a line in 2 dimensions?
Y equals mx plus b.
So that's one way to write a line. Y equals mx plus b. That's in 2-dimensional space. And another formula, another way to represent that line, you could write it in this more general form. Ax plus by equals c. Same idea. That one you just solve for y. Just isolated y. But it's the same idea. It's the same concept there. It's equation of a line. Okay, how about in 3-dimensional space? A line in 3 space. Anyone have any idea what the easiest way to represent a line in 3-dimensional space?
MZ on the
Did I hear add a z?
ax plus by plus cz.
So this is the natural place to go because that's the simplest linear equation in 3 variables. The simplest linear equation in 2 variables gives you a line in 2 space, so it's natural to sort of say, oh, well then the simplest equation that's linear in 3 dimensions must be a line, but that is not a line. You should have learned in college algebra what that is. What is that object?
A plane.
A plane. The plane. That is a plane. So this is a plane, not a line. So if the simplest equation in 3-dimensional space, the simplest linear equation in 3-dimensional space, doesn't lead us to a line, it leads us to a plane, we need another way to represent curves. Because we live in 3-dimensional space. Yeah, let's close that. We live in 3 space. Most of our applications are in 3 space. And most of our applications involve a line or a curve of some sort in 3 space. If you're dealing with, you know, rockets or balls being launched or any of that stuff, you're talking about a curve in 3-dimensional space. So if we can't even represent a line, we can't represent, you know, an arc with this rectangular coordinate system. So we need another type of equation, and that's where parametric equations come in. There are other reasons that we like parametric equations versus Cartesian equations. These things are Cartesian equations. But the primary thing, in my opinion, is that we need these parametric equations to represent paths in space. That's what most of our applications involve. Now, when we get to these parametric equations, what we're going to see, there's also something called the orientation. So if we have a curve in Cartesian, there's no orientation to it. If you graph a parabola, you get your parabola. You don't think about the points being plotted in a direction. When we get to parametric equations, what we are going to see is that they will have, not all parametric curves, but there's some conditions, but we will have a positive orientation, which means that you can tell the direction that the points are plotted. So orientation or positive orientation just means the direction the points are plotted. Now, not every curve is going to be orientable. We'll talk about why later. But so here's the idea. Parametric equations, you have coordinate functions. And these coordinate functions are going to be a function of a new variable. Usually we call it t, the parameter. And t, usually in our mind, we think of it as time because often we're launching something and so we want to know where is it at time t. So that's going to be generally the way you conceptualize it in your mind, that you think of t as being a time value and you're going to have a start time and then you're going to figure out where it is in the future as it passes through space or whatever. So this is an example of parametric equations. That will end up being the graph. Let's figure out why. So the idea then is that we are super familiar with Cartesian. So what we generally want to do is convert these parametric equations to Cartesian, which means get rid of the t. Go back to x and y. That's what we've been graphing for many years, x's and y's. Now to get back to x's and y's, so we're going to eliminate the parameter. Often the Pythagorean identity is going to be helpful to get rid of the t. And we know that sine squared plus cosine squared is 1. So sine squared of any variable plus cosine squared of the same variable, we know that that's 1. Always. Doesn't matter what t is. That's an identity. That's always true. So when we look back up here, sine is equal to y, so sine squared is equal to y squared. Cosine is equal to x, so cosine squared is x squared. So this is going to be the Cartesian curve. So this is parametric. And then this is the corresponding Cartesian curve. That's a unit circle. So we're going to graph the Cartesian equation with dashes. The parametric curve is a subset of the Cartesian curve. The parametric curve might be the entire Cartesian curve, but not necessarily. It's often just part of it. So we graph the Cartesian curve with dashes or dots, and then we apply the parametric domain by plugging in some points. So there's the parametric domain. So we want to look and see, does that parametric domain somehow limit the graph to be just part of the Cartesian graph, or is it the whole thing? And in this case, we're going to see that it's limited. So usually we'll set up a table of values. We'll plug in our t, and every t value is corresponding to an ordered pair. So the time value corresponds to a point in two-dimensional space. So let's check. Certainly we want to plug in 0. Certainly we want to plug in pi. And you can plug in as many points in the middle as you need. Typically, if you're, and sometimes 2 points is actually enough. Like if the curve is not closed, like a parabola is not closed, the circle's closed. And with a closed curve, you absolutely need at least one more point in between 0 and pi. Usually we'll just pick the middle. Because we won't know what direction we're going unless we have a third point there to test. So let's see how this works. So t is 0. Come up here, we evaluate. Cosine of 0 radians is 1. Sine of 0 radians is 0. So the ordered pair is 1, 0. So that tells us that at time 0, we are going to be right here. Time 0 is right there. That's the point that's plotted. And now we come to pi halves. Plug it in. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we are at 0, 1 at pi over 2. And we certainly have a sneaking suspicion that when we plug in pi, we're probably going to be over here at pi radians. Let's check. Plug in pi, cosine of pi is -1, sine of pi is 0. So sure enough, we're there. So this is our location at pi radians. And now we connect the dots. So our parametric curve is that upper semicircle. Okay, so we just get the top half of that Cartesian graph. And the orientation is the direction of increasing t. So we usually will put arrows somewhere in the middle to indicate what direction the points are being plotted. So 0 to pi, that'll be our Cartesian, that'll be our parametric curve right there in red. Cartesian curve will be the whole thing, but we only get half of it. So that's how it works. The other thing that we want to keep in mind is that the t-value may or may not have a geometric representation with the graph. Here it clearly does. The t-value is representing the counterclockwise angle. Right? The t-value has a geometric significance here. It does not always, but here it does. So there it is. Any questions on that? So the main idea is that we start with our parametric equations, eliminate the t, graph the Cartesian, look and see if there are any restrictions, and then graph the parametric, and then indicate the orientation. Now, parametric equations also have another awesome quality to them. So tell me this, if you were to graph, if someone said graph this equation, what does the graph of that equation look like?
Vertical line. Vertical line, X.
Why are you assuming you're in two-dimensional space?
Because there's no.
If we're in one-dimensional space, isn't x equals 2 just a point? We don't know. Absolutely. If we were told that we were in two-dimensional space, I totally agree. But there's nothing about that equation that gives us we call it the ambient space, the space that the curve lives in. We could be in 3 dimensions. Anyone know what the graph of that would be in 3 dimensions? A plane. So we would go to x equals 2. Normally we do our 3-dimensional coordinate system this way. We would go to x equals 2, and normally when we draw a plane, we just draw the part that's in octant 1. But there are 8 octants when you break it into 3-dimensional space. You have 4 above the xy plane and 4 octants below the xy plane. Normally, if we have a plane, we try to just draw it in octant 1 if it's in octant 1. But, so when you see that, there's no indicator whether you're in R1, R2, or R3, or even something else. You just don't know. So in R3, it's the graph of this in R3, the set of all points where x is 2, y can be anything, z can be anything. So it gives you a whole plane. There's 2 degrees of freedom. Y and z aren't restricted. Right? If a letter is missing from the equation, then it's unrestricted in that direction. When you come over here in 2-dimensional space and you graph x equals 2, okay, y can be 0, y can be 1, y can be 2, y can be -1, right? Y is not in the equation, so it's unrestricted. So we call that an extrusion. If a letter is missing, you pull it in the direction, you pull the graph in the direction of the missing letter. So here, x equals 2, but then the y is missing, so you extrude it parallel to y. Down here, you plot the point 2, 0, 0. There's no y, so you extrude in the y direction. There's no z, so you extrude in the z direction. So missing variables mean they're unrestricted, and you can go as in both directions towards infinity in that coordinate direction. Either here, up and down, here in the y direction, here in the z direction. Now with parametric equations, all of that is revealed right here. This tells us, A, that we're in two-dimensional spaces because we have an x and a y. If we were in 3-dimensional space, we would have an x equation, a y equation, and a z equation. So for example, if we were given this, so if we were to say x equals cosine of t, y equals sine of t, and let's just say z is equal to t squared. Okay, there's 2 immediate things that I would conclude about this. First is that we're in 3-dimensional space, so we would call that R3, because there are 3 coordinates. Moreover, I would say that this is a curve, not a surface. It is a curve, not a surface, because there is one parameter. So one parameter means that we can only be going along a curve. If we were to graph a surface in three-dimensional space, which you'll do parametrically in Calc 3, you would have two parameters over here. You'd have an s and a t. So it might be cosine of t plus sine of t, sine of t times cosine of s, whatever. There would be two letters over there. So this tells us that we have a curve in R3. Now, if we were to try to graph this, anyone have any idea what the graph might be? So if you think, Perry?
It'd be like a spring compressed.
It's a helix, yeah, exactly. So the cosine of t, sine of t puts us on a circle, and then the t squared thing pulls us vertically. So we would end up getting an upper helix that goes up forever, but this z is always positive, so we wouldn't get a helix below the xy plane. We'd end up just getting this spiral above the xy plane, half a helix.
And if we didn't have a z defined on the floor, then it would just be a cylinder.
If this was a different letter, we can't have a surface unless there are two letters. So if this was an S, then we'd be filling in, we'd be filling in, yeah. So then we could get, a cylinder depending on what the restrictions on that variable are. Yeah, so that's the idea of parametric. That's what's so nice about them. A, you can graph curves in three-dimensional space. B, you know what space you're in. And C, you know whether it's a curve or a surface. So parametric is really nice in that way. It reveals a lot of information, way more than a Cartesian equation. So let's look at some more of these. So here's another set of parametric equations. Step 1, let's go Cartesian. Let's eliminate the t. Oh, we see trig functions. That's a clue that we want to use a Pythagorean identity. And we know that this Pythagorean identity is true for all angles. It doesn't matter if it's t or negative t or t squared, as long as the angle is the same, that Pythagorean identity holds. Does not matter, right? That's true for all angles. So then we come back up here, we say sine squared of negative t, oh, that's y squared. Cosine squared of negative t, cosine of negative t is x, so this must be x squared. So our parent curve, our Cartesian curve, is once again the unit circle. Graph it as dashes, and then we go and we have to figure out whether there's any parametric restriction from this domain. So every t value corresponds to an ordered xy point. So we definitely want the 0, we definitely want the pi, and then we need something in between when it's a closed curve so that we can tell which direction we're going. If we only had 2 points, we wouldn't know if we're going clockwise or counterclockwise. So if it's a closed curve, we definitely want 3 points. We plug in our 0 up here. Cosine of 0 is 1. Sine of 0 is 0. So this tells us that we're right here when t is 0. Then we plug in the pi over 2. Cosine of negative pi over 2 is 0. Sine of negative pi over 2 is negative 1. So this puts us down here when t is equal to pi over 2. And sure enough, when we plug in pi, cosine of negative pi is negative 1, sine of negative pi is 0. So we're over here when t is pi. We can now connect the dots, and we know that the orientation is this way, because that's the direction the points are plotted. So our initial feeling is, oh gosh, if we replace t with negative t, it just reverses the orientation. Not always the case. It's not quite that simple. Many times, if you replace t with negative t, it will change the direction. With the prior one, we were going counterclockwise, right? So when we had just a t, we were going counterclockwise. When we have a negative t, we're going clockwise. So it feels like that might be true, and it is sometimes, but not always. So if a question says reverse the orientation, this is one thing to try for sure. Let's check out this. So here we just switched the role of sine and cosine. But you should probably see really quickly that, oh gosh, it's the same parent curve. It's the same Cartesian curve, right? We know that sine squared of t plus cosine squared of t is 1. Sine squared, so that gives us x squared plus y squared equals 1. So again, we have that same Cartesian curve, the unit circle. Now we go to our t values. Let's figure out if the restriction on t gives us the entire Cartesian curve or just part of it. And so far in the prior two, if t went from 0 to 2 pi, do you see you get the whole circle? All right, you get the whole circle if we went 0 to 2 pi. Here we again are going to do 0, pi over 2, and pi. Plug in our points. So plug in t equals 0. Sine of 0 is 0. Cosine of 0 is 1. So we're at 0, 1. So now our start point is up here on top, North Pole. That's t equals 0. Plug in pi over 2. Sine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So then we're at 1 comma 0. That's where we are at pi over 2. It certainly feels like we're going to be down below at the South Pole when t is pi. Let's check. Sine of pi is 0. Cosine of pi is negative 1. So sure enough, we are down here when t is pi, and our parametric curve is the right half, and our orientation is clockwise. So these examples just give you a sense of how the same Cartesian curve can lead to all sorts of different parametric curves. And it also gives us a sense of how, so what this one did, if we compare it to the first one, so here we switched the coordinates, we switched the x and the y, and it also changed the orientation. We went from counterclockwise to clockwise. So that's another candidate. If a question says reverse the orientation, we have two choices right now. Replace the t with negative t or switch the x and the y. Sometimes one will work, sometimes the other will work, sometimes both will work. And there's also times where neither of those would switch the orientation. You'd have to do something more complicated. So any questions on this intro of how these things work? So nothing super complicated. Let's see, is that going to load? So you can go in Desmos and graph parametrically also. Parametric equations in Desmos, all you do is put two functions in parentheses with a comma. That's it. And so I wanted to restrict this one, so I said, with the brackets there, I said, okay, well, we're going to let t be less than or equal to a. And then down here, we're going to move the a around. So this is going to, as a goes to 2 pi, we get the full circle up there. Cosine comma sine, it's going to be the regular unit circle going counterclockwise. And then here's the second one we looked at. We switched t with negative t. So the orientation changes. There's t equals 0. We start over there at 1 comma 0, and we go that way. So you can play around with some of this stuff just to get a sense of how fiddling with these work. Now let's check out this one. So here, instead of cosine t comma sine t, we did this. Let's notice the difference. So here we're going to start over at negative 1, 0, and we are going to go clockwise and get the full circle. So lots of different options here. Yeah?
How would you show the orientation? Like, how would you save that?
That's what the arrows mean.
Oh, okay.
So when we put in these arrows, you don't have to use words. All we do is put the arrows.
Okay.
So those arrows say we're going to plot points in this direction. We're going to plot points in that direction. And we don't put them at the endpoints, especially if it's if they're included endpoints. We put them somewhere in the middle of the graph, just to indicate which direction we're going. All right, you all try this one. Try this parabolic one here. So come up with the Cartesian equation, and then graph it on a Cartesian plane and see if you are going to get what I get. What are y'all getting for your Cartesian equation?
Y equals x squared.
Totally obvious, right? You're eliminating the t. So
How do
the-
you know?
What's that?
How do you know?
How do you know what?
Like, I don't even know where to start.
So the first step is to eliminate t, eliminate the parameter. So with this example, in order to eliminate the parameter, we use the Pythagorean theorem. But for this one, we just need substitution, right? If x is equal to t, then we're going to plug that in down here. If x is t, then we're going to replace that t with an x, and we'll get y equals x squared. So step one for any parametric curve is get rid of the t. It might be with a Pythagorean identity, it might be with substitution, it might be whatever. Elimination method is also possible. So it's all that standard algebra stuff where you solve a system. And then our parametric curve leads to this Cartesian curve. The graph of our Cartesian curve is that dotted parabola. And then we want to look at the parametric domain. So the parametric domain will restrict the parametric curve. So it's really nice with parametric equations because you can restrict the domain very easily. Now here, we technically don't need to pick a middle point because this is not a closed curve. So it's going to, 2 points will be enough to get our orientation. When we plug in -2, we're going to have -2, 4. If we plug in 0, we're going to get 0, 0. If we plug in 2, we're going to get 2, 4. So this parametric curve is a portion of the parabola y equals x squared. It's going to stop, right? So this is t equals -2, this is t equals 0, and this is t equals 2. And to indicate the orientation, we just put a couple of arrows in. The direction is that direction.
That's only because it's an ellipse.
Say again?
It doesn't connect, it's not an ellipse.
Yeah, it's not an ellipse, it doesn't connect. So we only need 2 points.
If it did, then we would most definitely need that center
Then we would
point.
definitely need that middle point. Yep. So very easy to get a portion. So this you can imagine if you're using some sort of trajectory, very easy to have, t goes from whatever to whatever, t equals 0 to t equals landing time, all those physics applications.
If it wasn't equal to -2 and 2, do you use open circles instead of filled in?
Yeah, exactly. So if those were strict inequalities, we would use an open circle. Now this one down here has the same Cartesian curve, right? When we look at this, same Cartesian curve. So y equals t to the 4th, we can think of that as t squared squared. So this is going to be y equals x squared. So we get the same exact Cartesian curve, same dashed curve over here, but then we go to our t values and we say, okay, well, what's happening? Is there any restriction from those t values? So let's again do -2, 0, and 2. So -2, if we plug that in, yeah, 4, 16. So that tells us that at -2, we're at 4, 16. We're right here at t equals -2. When we plug in t equals 0, we get the origin. So t equals 0 puts us right down here. Now when we plug in t equals positive 2, don't we get 416 again? So t equals positive 2 puts us at the same place. So this curve does not have an orientation because there is a hidden point of non-differentiability. If you think in your mind, t is negative 2, this particle is coming down and it hits negative 2 and it turns around. In Calc 1, you could geometrically see points of non-differentiability, right? There'd be a corner or a cusp or a jump or something funny. With parametric curves, you cannot see. If you're imagining sort of the ball moving, like the very first section we did in this class, we were talking about linear motion. And when does the motion zero? Like if you have a parabola graphed in Calc 1, you can see up top that the derivative is 0. Right? You can see those points where the derivative is 0 or undefined. With a parametric curve, it can track back on itself, so you can't always see it. You have to do a little bit more analysis. So here, we would say that this curve is non-orientable. So this is non-orientable as it sits. Now, if you changed your domain and you said, let's just go negative 2 to 0. If you said, let's just go negative 2 to 0, then the orientation would be down. If you change the domain to be 0 to positive 2, then the orientation will be up. So this kind of thing is going to become important if we're trying to find arc length. If we're trying to find arc length, we need to make sure that no points are duplicated. Right? If we want truly the length of that measured arc right there, if we want to parameterize the curve and use it to find arc length, we have to make sure there's no extra points, that we're just going one direction and capturing all the points. So non-orientable as it sits, but if you change your domain, you could find two orientable curves that are part of this parametric curve. So it's very similar to what we were doing back when we were doing implicit functions. When you graph a circle, you know that a circle is not a function, but it is the union of two functions. This is a function. The upper semicircle is a function. It passes the vertical line test. And the lower semicircle is a function. So it's that same kind of idea that this parametric curve has two oriented parametric curves as part of it. But as it's given, so a parametric curve includes the two equations, if you're in two space, and the domain. The whole thing together is the parametric curve. So this parametric curve as given is not orientable. Okay, so then let's try to create, and this can be hard, to build parametric curves. We kind of have a sense for circles already, though. So this says find parametric equations for the following curves, including interval. So this says build parametric curves for a circle centered at the origin with radius 12, generated clockwise with initial point 0, 12. So take a look at the ones we've already done and see if you can figure out what the structure should be for this parametric curve. So we know we're going to have a sine and a cosine in here somewhere. How does the 12 come into play? How are we going to create something that's not just a unit circle? How are we going to create it to be a radius of 12?
Multiply them by 12.
Multiply them both by 12. Like if we had x equals 12 cosine of t and y equals 12 sine of t, that would give us a full circle of radius 12. So the coefficient in front of sine and cosine, if they match, you'll get a circle. Okay, so now we want to go clockwise. So we want to go that way. So what are we going to start with?
Sine of t.
So if we go sine t 12 and cosine t 12 in front, let's check. So first off, to check, we see trig functions. So if we wanted to eliminate that t, we would have to use a Pythagorean identity. That's sort of, hopefully that's obvious. So sine squared plus cosine squared is 1. We know that. That's always true, no matter what. What is sine of t equal to up here?
X over 12.
X over 12. So we're going to get x squared over 144. Cosine squared, same idea. If we want to solve for cosine, we divide by 12, so we have y over 12, but we're squaring it. So we get y squared divided by 144. That's equal to 1. Multiply both sides by 144, and yeah, okay, we get the radius, we get a circle centered at the origin of radius 12. That's what the equation of a circle centered at the origin of radius 12 looks like. So we've got the circle. Now let's check and make sure that we have the right orientation. So they said we want to have it start at 0, 12. So let's plug in some t values. So let's make sure. So if we start at 0, plugging in 0, sine of 0 is 0, cosine of 0 is 1. 1 times 12 is 12. So we're at 0, 12. All right, we're right where we want to be, 0, 12. That's t equals 0. Okay, now it says full circle, and we want to go clockwise. So let's see if we are still footing the bill here. So if we go to, let's go to pi. Let's just test pi. Sine of pi, 0. Cosine of pi, -1. So we're at 0, -12. So down here is where we are. And so you can see if we just plug in those 2 points, we don't know whether we're going clockwise or counterclockwise. We would need a point in the middle. So let's pick a point in the middle. Pi over 2 is the obvious candidate. Sine of pi over 2 is 1. 1 times 12 is 12. And then cosine of pi over 2 is 0. So 12 comma 0. So we are over here when t is pi over 2. All right, good. So we are now going clockwise, starting in the north, starting at the North Pole. So sure enough, that is our thing. Let's see. Will I be able to draw a circle? Not too bad. Okay, so, all right, now the next thing, we need a domain. If we want just this, it says a circle. It doesn't say a circle with extra points, so we need to stop the domain. So what do you think we want our domain to be?
Starts at 0.
Certainly starts at 0.
And then 2 pi.
2 pi, and we don't want to include the 2 pi because then we would have a circle plus a point. So usually we're going to have a half open, half closed interval if we want a closed curve. So we want to include the 0, but we should exclude. Sometimes people are sloppy about that, but that's what we would want to do to be precise. That will give us the full circle.
Does it matter which point you include?
Nope.
You always include the first or
0 is usually the natural one to include, but if the goal is just one full circle, you could do it any way you
And
want.
that's just from the front because they said they wanted a full circle, correct?
Mm-hmm. That's right.
Starts at 0.
All right, let's talk about the exam a little bit. The 2 people that aren't here, I already know they're not coming. So it's Bryce's birthday. Who would go to class on their birthday? Not Dustin,
Not me.
right? So, a couple of the dumb things. couple of the dumb things. First off, you cannot show that a series converges by looking at a limit of a sub k. So I saw this multiple times.
Try.
So if we have a series, let's just suppose we have 1 over k factorial. If you just take the limit of a sub k here, that's the limit of this, at least 5, if not more, said, oh, therefore converge. That was the very first thing we learned in chapter 11, or chapter 10.
Isn't that just the divergence test?
That's the divergence test. This is totally false. This just means inconclusive, right? It's necessary that a sub k goes to 0 if you're going to add up an infinite collection of numbers. It's necessary that they go to 0, but that's not enough. The harmonic goes to 0, but that adds up to infinity. So I saw that a bunch. Muy mal. I even saw this algebra 1 mistake. This algebra 1 mistake, I forget exactly what the problem was. It was something like k plus 1 to the half or something, and I was told that this was equal, it was something like this. Really? Whew. Not happening. That is false. You cannot distribute a square root over a sum or a difference. You can only distribute a square root over a product or a quotient. Cannot do that. And then when you're making mistakes like that, you gotta weed those out. You know, if you're tending to make bad mistakes that are, algebra especially, you can't go anywhere from there. The problem's completely hosed if you make that mistake right from out of the gate. Another thing, if we have an alternating series, let's suppose we have an alternating series like this. And I think the one on there was a k factorial, actually, like that. If you're trying to show that that converges by, first off, if you have an alternating series, there's only one test. What's the test if you have an alternating series? Alternating series test. Or maybe this was a case, I don't know, there's a couple of different scenarios. Let's look at that one. This does not converge because it's a p-series. That is not a p-series. Saying this is not correct. That series is not a p-series as it stands. It's an alternating series. It's not a p-series. I agree that this is a p-series. So if you did this here, 100%. This is correct. That is correct. This is not correct. The only way to show that an alternating series, well, there are two ways, but the primary way you show an alternating series converges is with the alternating series test. You do the 2 steps. The limit of a sub k is 0, and the terms are decreasing. Right? Alternating series test has 2 steps. Now, technically, it is possible to bypass the alternating series test and say, oh, let's consider this. So let's take the absolute value, and this converges, and there's a theorem, which would then have to be referred to, that says if you have the series of absolute values converging, then the series with the negatives also converges. You could use that theorem, but those of you that did this weren't even thinking about that theorem. It was obvious. So this, to show that this converges, you use the alternating series test. Okay. There was another painful thing. Let's see. Oh, this. So let's suppose we have this. And you want to differentiate. So if you want to take the derivative of that, -1 to the k is a constant. When you take a derivative, constants float. When you take this derivative, the negative 1 to the k, nothing happens to it. It's a constant. It's like 5 or 10 or pi. Nothing happens to it. That is the derivative. Right? Constants just float when you're taking derivatives. A couple of people put the k in front of the negative 1 and then subtracted 1 from the exponent of negative 1. What's the derivative of a constant? 0. If you take the derivative, if you have f of x equals 2x, right, the derivative is 2. Like we don't take a product rule there. Constants just float down through our derivatives. So there was that. What is a power series? Somebody tell me the structure of a power series.
Constants multiplied by powers of n.
Constants multiplied by powers of x. So if you have something, so like let's suppose we have a power series that looks something like this. Let's just suppose we have a power series that looks like this. So what is the center of this power series?
Negative 2.
-2. If you look at f of, say, x squared, and just do this kind of thing, is that a power series? No. That is not a power series. That is not a sum of powers of x. Right? X squared plus 2, that is certainly it's not a power series, and it's definitely not a power series centered at -2. Right? This center here is -2. That is not a power series, and if you somehow convinced yourself that it was, and someone said, well, what's the center? It's definitely not -2.
Well, actually, I figure out, like, you know, like 2x, the product rule could work. Because first derivative last,
Yeah, you could use a product rule for this.
and then like time plus last derivative first.
And you could use a product rule for this too if you wanted. Anyone that's doing a product rule for the derivative of a constant times a function, you must be bored, right? That is so
You
unnecessary.
gave us the whole test in time, we're using the whole guy.
We're using every skill we've ever learned.
Whole thing.
Is everybody clear that this is not a power series? A power series is a sum of powers of x. You should be able to write it as constant plus constant times x plus constant times x squared plus constant times x cubed. And that is not what's happening right there.
Or it could just be like, you take and show your work too literally.
Yeah, show every single detail, every minute step. So this is not even a power series. So the on this exam, so this is the one where you're supposed to take derivatives. The one I told you was the hardest one. So this was number
12, I believe.
12, thank you. So if you want to get to G from F, substitution, yes, it's true that G is equal to f of x squared, but it's saying find a power series centered at 1. If you just plug in x squared, you do not have a power series centered at 1. But if you take the derivative of f twice, so if f is equal to x to the -2, and if you take two derivatives, I also saw this mistake. If you bring down the exponent and subtract 1, what do you get for your exponent?
-3.
-3. Subtraction. So, and then if we take the second derivative, we are going to see 6x to the -4.
Yeah.
Now, our function g was x to the -4. So we divide by the 6, we get that g is f double prime divided by 6. So if we look at the key for 12, we're going to get, we take two derivatives, we isolate the 1 over x to the 4th because that's g, so we get f double prime over 6. And then the derivative of this, that part's constant. The -1 to the k and the k, that's constant, so it just floats down. Constants just float when you take derivatives. as long as you have a function in there. And then the derivative of this part is right there. Bring down the constant, subtract 1. So we did that twice. And we do have an adjustment with the index. As you take derivatives, you bump the index by 1. And so then g, we said, is f double prime divided by 6. So there's f double prime divided by 6. That's the power series centered at 1. And then we test both endpoints. Now, here, this one is, so what we said was that with the alternating series test, the first part of the alternating series test is the divergence test. So this one's actually not an alternating series because you have an even index up here, so this is always a 1. So the divergence test, there's your a sub k, whether it's an alternating series or not, that's a sub k. And the first step of the alternating series test is the divergence test. A sub k has to go to 0 or it diverges. So you could say by the alternating series test, or you could say by the divergence test, because that's a subset of the alternating series test. The binomial one, that one overall was okay.
As long as you don't forget the negative.
Yeah, as long as you don't forget the negative, and as long as you do this substitution here.
I forgot the negative.
Yeah, you had a bigger interval than you needed. The other ones down there, let's see. One thing here, as soon as you find your term that's less than whatever the prescribed error is, you add everything in front. You don't include that error term. As soon as you get to that error term, you add everything else in front. So take a look carefully at that key and let me just glance up higher and see if there's any other mistakes that I want to call out. Oh, on the first one, let's see. So on the first one, these are geometric series. So you can certainly here use the divergence test, totally fine. That diverges because the limit of a sub k is infinity. That's totally fine. But I was hoping that you were seeing it as a geometric series. The geometric series says that if r is less than 1 in magnitude, you're going to have convergence, so like that. And r greater than 1, you're going to have divergence. Divergence test works though, but.
But didn't the instructions tell us to use the divergence test?
Not on number 1. Number 1 said geometric series. Another mistake I saw many times. On number 3, the integral test has nothing to do with the number 1. It has nothing, this converges, but has nothing to do with the fact that 1/6 is less than 1. That is not why it converges. With the ratio test, the root test, and the geometric series, less than 1 converges. Right? Geometric, root, and ratio. Integral test says what?
Is it positive or real?
Is it a positive real?
Does exist. Good.
The integral test says that if you do the integral, the improper integral, and you get a number, so the improper integral converges, then the series must also converge. So there's no threshold with the integral test of, oh, if it's less than 1 it converges or greater than 1 it diverges. That's with root, ratio, and geometric. For integral tests, it's 2 separate things. We've got the series and we've got the integral. And if the integral converges, the series converges. If the integral diverges, the series diverges. But there's no threshold of being bigger than 1 or less than 1. So it's just that this integral converges because you get a positive number. If you get a number here, that means it converged, positive real. So if that converges, then the other one converges also. We're talking about converge in 2 different senses though. Integral converging, series converging. So they both converge or both diverge. But it's not because of the 1. It's not less than 1 or greater than 1. And here, there was another error I saw a couple of times. Here was another one of these types of errors here with the exponent. When you're integrating, you add 1. Negative 2 plus 1 is negative 1, not negative 3. So that's going to be a negative 1. And you use reverse chain rule. You have to divide by the derivative of the base. The derivative of the base is 2, so we have to divide by the 2. So the negative is coming, so when we integrate here, we're adding 1 to the exponent and getting negative 1. We divide by the negative exponent, which is the negative 1. But then we also have to divide by the derivative of the base. Divide by 2. I did see an error down here on, this one didn't show up a lot, but there, it did show up. Let's see, where was it? Was it on 6 or was it on 5? I think it was on 6. Okay, yeah, 6, actually there was a handful of you that chose the wrong b sub k. The b sub k here is 1 over k. Is not 1 over k squared. When we are finding our b sub k, we eliminate the fluff. And so if we look at that numerator, square root of k squared minus 1. So we have this, and that was k squared. This is the fluff, negative 1. That is meaningless in terms of convergence or divergence. And when we're dealing with positive numbers, what is the square root of k squared? K, when we're dealing with positive numbers. And then we cancel out a k. There is your b sub k. Okay. Let's suppose you did it wrong anyway and you pick 1 over k squared. Does the series 1 over k squared converge or diverge? Converge. Series 1 over k squared converges p series p equals 2 bigger than 1. You cannot take a convergent series and then conclude divergence later on. If you choose a convergent series, you're trying to show convergence. If you choose a divergent series, like 1 over k, you're showing divergence. So a few of you had a 1 over k squared and then concluded divergence. You cannot use a convergent series to show divergence. Bigger than diverging diverges, smaller than converging converges. So you've got to have those lined up. They can't mix and match.
Well, but we can try.
You can try. There was definitely some creative trying going on. Lots of creative trying.
Well, what do you see? Like with creative tries done?
Creative try was using 1 over k squared as a convergent series, but then concluding divergence. You cannot show a series diverges with a convergent series. Can't do it. Can't do it. Okay, let's take a break. And then we'll jump back into chapter 12, something less intense.
We passing this test,
start
boys.
recording yet.
Can you Michael's X?
Okay, so lines in 2-dimensional space are going to lead us to lines in 3-dimensional space. Reality, lines in 3 space.
Can our test just be solved y equals x?
No. No silly questions. So the parametric equation for a line, if you've done some vector stuff, you can do this with vectors. So I'll show you both perspectives, but the idea with the parametric equations for the line is that both the x-coordinate and the y-coordinate are both linear. So what we're going to think about is a point that's on the line, which is going to be the x naught, y naught. So there's the x naught and there's the y naught. And then the slope of the line is b over a. And normally when you think of slope, you think a change in y over change in x. And the change in y part, the b part, that's going to be the coefficient of t for the y-coordinate. And the a part of the slope is going to be the coefficient of t for the x component. Okay, so those are going to build a line. All right, let's just look at it from a vector point of view for a moment. So the idea here is that we're going to look at vector v, and that's the vector that's going to go from here to there. So it's that red vector. And a vector is just a directed line segment. So it has initial point and then terminal point. And the vector just connects the 2 points. So there's vector v. Vector r sub 0 is the initial vector. R sub 0 is this vector that points to the initial point on the line. It's like the origin. It's where we're going to start. So this is just any point on the line. Typically, we think of it as the origin of this new line. And in order to get points, what we do is create this linear equation right here. This is a vector equation, though. R is a vector, R sub 0 is a vector, V is a vector, and then T is a constant. It's our parameter. So this is how we add vectors. We add the x's and we add the y's. So this T gets distributed, and we add, and those are the 2 coordinate equations that we saw up here. So if you're used to doing vectors, you can think of this line concoction as just a sum of 2 vectors, if you want. If you have never done vectors, and you don't want to think about them now, then just use these. X naught plus AT, Y naught plus BT. All right, so here we have parametric equations right there. And we want to graph this. We want to figure out what the parametric curve looks like. So we have a couple of things we could do. We could say x sub 0 is the constant from the x, which is 0. Y sub 0 is the constant from the y, which is -4. A, which one does A come from? So if we come back up here, remember that the A is the slope here. So its slope is change in y over change in x. And the A is in the bottom, so the A comes from the x, the B comes from the y. So A comes from the x, so that's going to be a 2. B comes from the y. So we have that. And if we wanted to write this equation then using point slope, everyone remember point slope? Y minus y0 equals m times x minus x0. So y plus 4, so y minus y0, equals the slope, which we said was 3 over 2, times x minus x0. So there is the equation in slope-intercept form. We'd have 3 halves x minus 4. So there it is in slope-intercept form. If we wanted to do it graphically, which is what we're going to do now, we have a couple of choices. So we're going to graph the parent curve, the Cartesian curve, by eliminating the parameter. Well, we eliminated the parameter by using sort of the y's and the x's that were given. You could also just go old school and do what we did in the last problem. You could do that. You could treat this as a system and say x is equal to 2t, y is equal to 3t minus 4. What do you think you're going to use to eliminate the t here? What's the easiest way? So we're going to solve this x equation for t, we get x over 2, and then we plug it into the lower equation, and let's just see if we get the same thing.
Yes.
And sure enough, we get the same thing. So we could sort of ignore some of the concept of a line and just go with what we already know. So that's going to be the equation. -4 is the y-intercept, and the slope is 3 halves, so we're going to go up 3 and over 2. So that's going to be the equation of the line. This board, you can't do dashed lines, though. So the parent curve is going to be this long line right here. Not terrible. Oh, maybe I can graph it in just like a light color, and that will be better. So let's graph it with this. Really? So if we graph it like that, so that's the parent curve, but we have a restriction. We're told that t can only go from -10 to 10. So let's come over here and look at our table of values. So every t value creates an ordered pair. Let's just pick 3 points over here. That should be enough. When t is negative 10, looks like x is negative 20 and y is negative 34. And then 0 comma negative 4. And then when we plug in 10, 20 comma 26. So, well, this is perfect. We'll just assume this is not to scale. Not to scale. So there's 20 comma 26. And then this would be negative 20, negative 34. So the Cartesian curve is really the entire line, but our parametric curve is just part of it. So maybe I'll put some orange dashes up there to indicate that this goes on forever. That makes sense? So a line parametrically has 2 linear components. Or at least if both are linear, you will get a line. You can't have a line where one of them is not linear. It's possible.
No, please don't.
But you will get a line if both are linear. That's the easiest way to do a line, if both are linear. Okay, so let's take a look at this one. So again, we have a couple of ways. We want to identify, let's do this one both ways. Let's think of it as a vector also. So x sub 0 is the constant from the x, y sub 0 is the constant from the y, a is the slope from the x, and b is the slope from the y. So those are all our pieces. So that tells us that we're going to have this set of parametric equations. So 6 minus, I need to put it x equals. So x equals, x sub 0 is 6 minus t. And then y is going to be y sub 0, which is negative 3, plus b times t. So we could do it that way for sure. So those are, so we see that that's where all these pieces come from. And then if we want to put it in slope-intercept form, we're going to substitute. So if we solve this one for t, we're going to get 6 minus x. And we plug it into the bottom equation, so we have that. And so then we're going to get y equals negative 3x plus 15. Let's check some points to make sure that everything is doing what we want it to do. Our domain is given to be negative 5 to 5, so let's go ahead and do that kind of thing again. And if we plug in negative 5 into our parametric equations up here, negative 5 for the t is going to give us 11. Negative 5 in there is negative 15 minus 3 is negative 18. Plug it in 0 should be 6 comma negative 3. Plug it in 5, I'm seeing 1 comma 12. Does everyone agree with those? So those are the end points and a point in the middle. And on the last one, I just remember we didn't do orientation.
Yeah.
What is the orientation on this one?
Going up.
Up to the right. Does everyone agree? And we started down here at negative 20, negative 34, and then we went to 0, comma negative 4, and then we went up here. So orientation is this direction. So when we start plotting our points, we will have 11 comma negative 18. Let's just assume that that's 11 negative 18. 6 comma negative 3. Put it right there. And then 1 comma 12. Oops. I'm going to have to rearrange these a little bit. Let's move this point. Make sure it's a line. And we've got our line, so that's our Cartesian line. Okay, and then our parametric line is just part of it. It's going to go between those 2 points. And what orientation? Are we going up or going down? So we started at 11, negative 18. So this is 0.1, and that's 0.2, that's 0.3. So we are going in the up direction. That'll be the orientation. Okay, so let's focus. A lot of times we don't want an entire line and we do want just a segment. And frequently we're given the points that we want as the endpoints. So here's where, in this context, it's usually a little simpler if you understand some vectors. But we can still do it the same other way where we're just, remembering these two formulas and putting the stuff in. So if we start at 0, 0, x naught and y naught are 0, x naught and y naught are both 0. Now, we need, in order to get b and a, we need the slope here. And we find slope by doing change in y over change in x. So this is going to be 8 over 2, which is 4. You can think of it as 4 over 1. Now we could pick different values of a and b. As long as b over a is the slope, it doesn't matter what you pick. In other words, parametric equations are not unique. So let me show you what I mean by that. We could pick that. Oh, do I have it backwards? So b over a is the slope. B over a is slope. So b is going to be the 4, a is going to be the 1. So let's take a look at the picture here. So we're going to start at the origin, and we're going to go to 2, 8. So start at the origin, we're going to go to 2, 8 right there. That's our line segment that we want. So t equals 0. Let's write our equations first, then we'll see that t equals 0 is going to be the origin. So our equations are x equals x sub 0, which is 0, plus a times t, so that, and y is y sub 0, which is 0, plus bt. So those are our parametric equations. If we simplify it just to t and 4t, tell me what the t interval has to be here.
0 to 2.
Does everyone agree? 0 to 2? If you want to end at 2, 8, that 0, start at t equals 0, this is going to be t equals 2 up here. Does everybody agree? So we're going to go from 0 to 2. So if we plug in 0, we get 0, 0. If we plug in 2, we get 2, 8. Let's do it a slightly different way. Let's suppose that we chose slightly differently. So let's suppose that we chose as our parameterization, instead of this, so this is the one we chose for here. Let's choose a slightly different one. Let's pick y and x based on that. So if we base it on that, then we still have the x sub 0 and the y sub 0 equal to 0, but x is equal to
2t.
So this is going to be a times t, and this is going to be b times t. And then what are the t values going to be?
0 to 1.
Yeah, 0 to 1. So we still are going to have the same orientation. We're going from the origin up. But we have two different parametric equations, right? Two different sets. So parametric equations are not going to be unique. This t value goes 0 to 2. This t value goes 0 to 1. So there is some flexibility when you're looking at that. Now here is the, let's do this second one totally from a vector point of view. So here's how I would do this from a vector point of view. I would say that, okay, we're looking for the equation of a line segment R of t, is going to represent that function, that vector function, and it's going to be the initial vector plus v times t. So this is essentially the vector slope-intercept form. It's essentially that. So r sub 0 is going to be the initial point. So r sub 0 is the initial point written as a vector. So a vector and a point have a very close connection. If you draw your vector in what they call standard form, that means it emanates from the origin. And so if you emanate from the origin, the point and the vector are the same if you come from the origin. And now v is found by doing this. So v is it's the analog to slope. Vector v is the terminal point minus the initial point where you write both of them as vectors. So it's going to be the terminal point, 6 comma negative 16, minus the initial point where you write them both as vectors, which just means brackets instead of parentheses. And if you subtract, you do it term by term. 6 minus minus 1, negative 16 minus minus 3. So this will be your direction vector. It's the direction that the points are being plotted, times t. And now you distribute the t to each component and then add. So it's negative 1 plus 7t. And it's negative 3 minus 13t. So that's how you would do it as vectors, which you can do it that way. If you're familiar with vectors, that's kind of the most slick way to do it. If you don't want to deal with vectors, you could do this. You could say we're going to start at negative 1, negative 3. And then slope is going to be the change in y. And so you would do this kind of thing. I think I did too. Negative 16 minus minus 3. So it's negative 16 minus minus 3, which is going to give us negative 13. And then 6 minus minus 1 gives us 7. And then this right here is the b, and this is the a. And that leads us to the exact same equation. So a is 7, b is negative 13. So we do negative 1 plus 7t, and we do negative 3 minus 13t. So either way, you can just sort of remember the parametric equations for a line, or you could sort of create them with this vector idea. Now, the nice thing about this vector idea here is that the domain is always automatically 0 to 1. If you do it with that vector technique, it's always going to be 0 to 1. If you use this slope idea, it will always be 0 to 1 if you don't reduce the slope. When we reduced the slope, our interval changed. And it changed exactly by the factor that we canceled between the b and the a. Right, we canceled out a 2, right? Divided top and bottom by 2, then we had to double the time interval. So here, if you don't do that, if you don't simplify this fraction, in this case it doesn't simplify, you'll always have an interval of 0 to 1 for your line segment. So 0 to 1 is going to be the default line segment if you don't simplify. So it's usually easiest not to simplify. So vector or using those equations, doesn't matter. Now, if we wanted to graph this, we just do what we did. We're going from this point, stopping at that point. The points are going to be plotted in that direction. And those are the parametric equations. Let's go to calculus. Why not?
Yes.
Whenever we have a curve, we want to know stuff about the curve, like its rate of change. Right? Ooh. So, calculus on a parametric curve. Pretty simple. Take the derivative of the y, take the derivative of the x. Change in y over change in x. Shocking. That's it. So here, if we want dy dx, it means what it's always meant. When you think about your parametric curve, it's just a curve in two-dimensional space. Dy dx means the same thing as it always has meant. Slope of tangent. So we do what that says right there. Take the derivative of y, and we get 8 cosine of t. Take the derivative of x, we get minus sine of t. So there's the derivative. The one change is that back in Calc 1, whenever you took the derivative of a curve, you got a function of x. Now we have our derivative as a function of t. It's a function of this parameter. And if we want to know what the rate of change is, we no longer are plugging in an x. And so what we're going to do is this kind of thing. We're going to put an evaluation symbol to indicate that we're evaluating at t equals pi over 2. Like if you were doing a derivative, like normally you would do this kind of thing in Calc 1, but this would represent an x. So we can't use this notation. Can't use that notation. So we're going to use this notation that indicate that we're using a parameter value, not an x value. So that parameter value is pi over 2. So we literally just come in here, cosine of pi over 2. So we're just going to do kind of what it implies we're going to do. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get the slope is 0. So what does that mean? If the slope is 0, what kind of tangent line do we have? Horizontal tangent line. So this tells us at pi over 2, we have a horizontal tangent line. So then we would go to the parametric curve and figure out, well, where are we at pi over 2? Right? So we'd have to go back to the parametric equation. So if we wanted to, if we wanted to interpret this, we have a horizontal tangent when t is equal to pi over 2. Okay, so if we want to know the ordered pair where that tangent line is horizontal, what do you think we're going to do with this t value?
Plug it into the original equations.
Plug it in right here. So the x comma y would be what? When t is pi over 2, cosine of pi over 2 is 0. Sine of pi over 2 is 1, multiplied by 8. So 0 comma 8 is where we have that horizontal tangent line. Let's draw this because this is slightly different than what we've looked at. If we wanted to draw this, we know that sine squared plus cosine squared is 1. What is sine squared in this case for this parametric curve? So if we isolate the sine, we get y over 8, so y squared over 64. And then the cosine is just x, so this is x squared. So what kind of curve is that?
It's a circle.
Close. So if both coefficients are the same, we get a circle. But because this coefficient is 1/64 and this coefficient is 1, we get an ellipse, we get a squash circle. So when we go to graph it, it's certainly going to be centered at the origin. And if you go under the y's, you're going up to 8 and down to -8. If you go under the x's, you're going left and right to 1. To -1 and +1. So this is going to be our ellipse. Right there, more or less. So that's going to be, that's not the best ellipse. I guess I can pull it that way too. No, that's not too bad. Okay, so there's the ellipse. That's the parent curve or the Cartesian curve. Now, we said 0, 8 is where our horizontal tangent is, so that's up here. That's the horizontal tangent, right at the top at 0, 8, or when theta was, or t was pi over 2. How about orientation on this curve?
We don't have a distance, right? Oh, wait, no.
So if we wanted to, where's t equals 0? So t equals 0 is going to be
1 and 0.
1 and 0. So there's t equals 0 right there. And t equals pi over 2, I think we just observed already. T is pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we're up here at t equals pi over 2. And we can kind of see that t equals pi should probably line up right there. Let's just double check. Plugging in pi, cosine of pi is -1, sine of pi is 0, so yeah, we're right there. So the orientation is in this direction, counterclockwise. Yeah?
But since we don't have the parameters for t, should we mark it as such, or do we just do a Cartesian?
So this whole problem just said figure out what the derivative is at pi over 2.
Gotcha.
So there are domains that are explicit and domains that are implied. So if we just graph like y equals x squared, and we don't indicate a domain, then there's sort of the implied domain is all real numbers. And the same thing is true of parametric curves. If we were to graph this, the implied domain would be 0 to 2 pi, excluding one of the endpoints, so that we would get one loop of the ellipse. So, but in this case, we're just sort of graphing it to kind of make sense of that horizontal tangent.
Gotcha.
Okay, how about here? So you guys try this one. Find the derivative of this parametric curve, and then find the slope of the tangent when t is -1.
And graph.
Nah, you don't have to graph it. I mean, it's nice to graph it just to get a sense, but no need. The main thing with these derivatives is that you do y over x, kind of like we always do for slope. So we just take the derivative of the y, take the derivative of the x, and there it is. That's dy dx. So the one change is that this dy dx is not a function of x, it's a function of t. So if we want dy dx at a t value, we indicate that with this evaluation symbol. All we do is plug it in, and there's our slope. 3/2. So that's the slope of the tangent when t is -1. Now again, geometrically, if we wanted to figure out where that is, it's not obvious what the x value is, but if we plug it back in here, we would say, oh, this is at -2, comma, -2, comma, -1. -2, -1. I almost fell for it.
Nothing what?
I'm saying the wrong thing out loud.
You said +1 there, and I almost agreed.
I can't read.
So we're plugging this -1 back in for each of these t values to get that ordered pair. So if we were to graph it, this is going to be a cubic, and that would be where the tangent has a slope of 3/2. So let's actually find the equation of a tangent line. So once again, we've got a parametric curve here. There's our parametric curve. And if you look at the graph, I plotted the graph for this parametric curve. And when t is 2, we're going to be at this point right there. So here's where we are when t is equal to 2. That's where we're going to be. So if we want the equation of the tangent line, well, we know that we need dy dx. We need the slope of the tangent line. This is going to be 3t squared plus 1 over 2t. So we take the derivative of the y with respect to t, that's 3t squared plus 1. We take the derivative of the x with respect to t, and we get that. But then we need to evaluate this, so we're going to have dy dx evaluated at t equals 2. So we're going to get 13/4. So that's going to be the slope of the tangent line. What about our point of tangency? So the point of tangency, we take the t value and plug it into the parametric equations. That will give us the point that we're interested in, the point where we're finding the derivative. So plugging in the 2 there gives 4 minus 1, which is 3, and 8 plus 2, which is 10. So now we have everything we need to find the equation of the tangent line. The equation of the tangent line, we use point-slope formula. Y minus y1 is equal to slope times x minus x1. So we're going to have y minus 10 will be 13/4 times x minus 3. Back to algebra. Point-slope formula. If you know a point and you know the slope, you can build the line. And if usually we like writing our lines in slope-intercept form because it's most revealing. So we would end up with, multiply this by 3, we're going to have negative 39 over 4, but then we add 10, 40, 40/4.
Oh no, 1/4.
1/4. 1/4 total. So there is the equation of that tangent line, which if we were to draw, it's kind of hard to draw it here, but it would be right there. So that's the equation of that tangent line. Any questions about finding that equation? So we use the new derivative idea, y prime over x prime, evaluate the derivative at our t value, gives us the slope of the tangent at that t value. Where are we? We take the t value, plug it into x and y to get the location of that tangent line. Once we have the location and the slope, we use point-slope formula, and we can create our line in slope-intercept form. Take all we know and get that. All right, let's try another one. So we've got this parametric curve here, and we've got this point that we're interested in. Is it clear that this point is 1, 0? No, if we plug in t equals 0, e to the 0 is 1, natural log of 1 is 0. So there's our point. And we're trying to find the equation of this tangent line right there. We want the equation of that tangent line. So we need the slope. So the slope of a tangent line, the slope of a parametric curve is going to be y prime over x prime. So y prime is 1 over t plus 1. X prime is e to the t. So if we simplify this, there's the derivative equation. So that'll give us the slope of the tangent line at any t value for which the curve is defined.
When you plug in 0, you get 1.
And if we plug in 0, so we're going to come over here and say, okay, the t value that we're interested in is t equals 0. That's we're asked. Plug in t equals 0, and we get 1. So the slope of the tangent line is 1. At this point of tangency, 1 comma 0. So we build our line by doing y minus 0 equals m times x minus 1. So there is our equation of the tangent line, right there. So this line here, can I tilt it a little bit? Oh, there's the rotation. Get it right through -1. That's pretty close. So the y-intercept is -1 right there.
Fun.
Fun!
Fun.
Any piece of that that's not logical? Or that you're not sure about? Okay, so sort of back to Calc 1 with parametric curves. Let's do arc length. So arc length we've looked at already in this class, and the formula is pretty similar to what it used to be. It's a little bit different though. So once again, the book introduces extra letters, which is kind of unnecessary. If you want to boil this down, I would think of this, instead of introducing an f and a g, why don't we let x just be x and y be y? Instead of using new letters, you're going to have x prime squared and y prime squared. So if you want to kind of use more concise notation, I would think about this, x prime squared plus y prime squared dt. Okay, so let's just think about this formula for a minute. Recall back that if we're dealing with a curve, so if we think about a curve, let's say in quadrant 1 right there, dx, that's the x differential, and dy is the y differential. So the dx, if we draw this little triangle right there, if we draw that, dx is this direction, dy is this one right there, and then ds is diagonal. ds is along the diagonal. So it creates this Pythagorean identity. Our independent variable is now t. So what we're going to do is create this equation here where we insert a dt squared because we need it. If you reduce this, you get back to here. If you take the square root, everything is positive. So square root of d squared is dt. And that's how we get that the integral to find arc length is going to be square root of x prime squared plus y prime squared. Because the integral of ds is s. And that's arc length. S represents arc length. So if we could, if we knew ds, if we had limits here that were in S, we'd be done. But we don't know what the S limits are. S is measuring along the curve. Don't know those S values. So we have to convert to t where we know t values. So let's try one. Okay, so the arc length is going to equal the integral from 0 to 2 of the square root of x prime squared plus y prime squared dt. So integral 0 to 2. X prime is what? 3. Y prime is? So this is going to be the square root of 9 plus 16 dt. So this is going to be 5 integral 0 to 2 dt, which is 5 times
2.
The length of the interval. So there is arc length. So the formula looks very similar to what we did way back in chapter whatever it was, long ago. chapter January. The only difference is that we now have two derivatives to look at. Back in that chapter, we said it was the square root of 1 plus y prime squared, or the square root of 1 plus x prime squared, depending on whether you were using vertical or horizontal. Here you use a little of each. A little of each. So let's find the arc length of this circle. We know a shortcut, of course, circumference, 2 pi r. But let's do it with the math. So if we're going to do it with the math, we're going to say arc length. We're going to integrate from 0 to 2 pi, square root of x prime squared plus y prime squared. So x prime, if we look here, that's -3 sine of t. Y prime is 3 cosine of t. So we take the derivative of the x, the derivative of the y, and now we have to square x prime, so we get 9 sine squared. We have to square the y prime, so we get 9 cosine squared. And what is 9 sine squared plus 9 cosine squared? 9. Right? Sine squared plus cosine squared is 1. And so we end up with the square root of 9, which is 3. And what's the integral of dt from 0 to 2 pi? 2 pi. So that's 6 pi. So that is the arc length. One loop of that circle. You could also do it geometrically. We know the circumference is 2 pi r.
Radius is 3.
Radius is 3, so 2 pi r is 6 pi. All right, so that formula checks out. It's working.
The math's math.
The math is working.
For that one, shouldn't we have it be one of the endpoints not included, though?
So there's no area there. So when you're integrating when you're integrating, you can exclude or include points. It's not going to matter with an integral.
Okay,
And the idea is that there's no area beneath the point, kind of thing.
understandable.
All right, so this curve, we have this parametric circle. So there's the x, there's the y. 0 to pi, we're going to get this half circle. At least it looks like a circle. All right. And you can try, if you wanted to graph that. It's not trivial. It's not like a circle centered at the origin. It's a little harder. But we don't need that here. We are trying to find the arc length. So S is going to be the integral from 0 to pi, square root x prime squared. So x prime is negative sine of t minus cosine of t squared. X prime squared plus y prime squared. Y prime is going to be negative sine of t plus cosine of t quantity squared dt. So x prime, y prime, square them both, add them together. Now we get to FOIL. FOIL. So we're going to get square root of, I'm just going to shorthand notation to S for sine and C for cosine. It helps clean up things a little bit. When you square this, you get negative sine squared. Negative sine squared is just sine squared. If you do the middle term, you do a times b times 2, so that's going to be a times b is positive sine cosine times 2, so you're going to get 2 sine cosine. And when you square negative cosine, you get cosine squared. Same idea here, negative sine squared, that's just sine squared. The negatives you get canceled out. The middle term is negative sine times cosine times 2, so negative 2 sine cosine. Plus cosine squared. So we have all that. We notice that we have a cancellation. And what's sine squared plus cosine squared? 1. So this all becomes equal to 0 to pi. 1 plus 1 is 2 underneath the square root.
Isn't it 2 sine squared? And then, oh yeah, never mind, you're good. I missed the part where you wrote 2. I heard you say 1 and I was like, I can't.
Yeah, 1 plus 1.
We're good.
And what is that equal to?
Pi square root 2.
Pi root 2. So pi root 2 is our arc length. Okay, let's go to, unless you have a question on arc length.
So does that mean that the radius of that circle is root 2?
Well,
The radius is root 2, but I think it's misrepresented.
say again?
Well, the radius is root 2 in that circle, but
Mm-hmm.
it should be half that, right?
Well, it's only half a circle.
Oh,
Half-
okay, I got you.
So the full circle would be 2 pi r, so that would be 2 pi times root 2, and then we divide that by 2. So this at least ostensibly looks like a circle of radius 2. We haven't proven that that is a circle of radius 2, but certainly looks like it. Certainly looks like it. Well, let's go to polar coordinates. Second to last section. Polar coordinates. Many of you have already seen polar coordinates. You'll do a lot of coordinate shifting in Calc 3. Polar is the simplest conversion. Instead of representing a point with Cartesian coordinates of x and y, we're going to represent points with an r comma theta, where r is distance from the origin and theta is counterclockwise rotation. So you can represent a point either in Cartesian or in polar. Doesn't matter, it gives you the same point. Now, the connection between them is given by these 4 equations, which all come from this triangle. Cosine of theta, x over r, sine of theta, y over r, Pythagorean theorem right there, tangent of theta is y over x. So all 4 of the equations that go back and forth come right from that right-hand triangle. So those go back and forth. Let's think about this conceptually for a minute. So r is distance to the origin, normally. Theta is counterclockwise rotation. The funny thing about polar is that we actually allow negative r values. So r, the absolute value of r is the distance from the origin, but if you have a negative r value, it means you go backwards. It means you go into the opposite quadrant, 180 degrees.
Love it.
We'll look at it in a minute. So all this stuff here, polar points are not unique. So this r value here, you could have a theta. Usually we want theta between 0 and 2 pi, but you don't have to have it between 0 and 2 pi. So the same point's going to be plotted if you do one rotation. If r is positive, your point's going to be out from the origin. But if your r value is negative, you're going to go opposite direction. Okay, so just keep that on the burner for the time being. We'll
On a test, you ask for a point and we give it plus 165. Will you mark us off?
plus a what?
165. Just looped around.
Usually you're going to be asked to find pi, angle theta between 0 and 2 pi. So if it says angle
No.
between, but if you don't, you can add as many.
It's game.
It's game.
Cool.
It is game. If I don't, it's game.
On the table.
It's on the table for sure. Okay, so those are the 4 equations that take us back and forth. When you get into Calc 3, so polar is in 2 dimensions, and there's going to be 2 new coordinate systems in Calc 3. One of them is called cylindrical, and one of them is called spherical. And polar is going to lead you to cylindrical, where you figure out a point in the xy plane, but then you go up or down to get into the 3-dimensional space, which will then lead you to spherical, which is super complicated. Okay, let's grab a point. Somebody give me a letter between A and F. B. So let's take that point right there. Let's represent this point in many ways. So B, you can see on this polar graph paper, is 3 units from the origin. So r comma theta. This is the standard representation. That's usually what we want. But given that there are a bunch of contrarians in here, the Declan types would say, yeah, that looks kind of boring, 3 comma pi over 4. Let's choose a positive r value, but a negative angle. Positive r value 3, negative angle would be what? Negative 7 pi over 4, exactly. So that's the same point with a negative r value. So going this way all the way around. Now let's choose a negative r value, but a positive angle. So then we would go, so positive angle, we would want to get to the opposite, so we're going to come over to here and stop right there. But then a negative r value is going to take us backwards, so this would be a negative r value and a positive angle. So all of these are different representations of B. This one is the standard. Now for hypercontrarians, let's have both be negative. If we want a negative r value and a negative angle,
Negative 3 pi.
yeah, negative 3 pi over 4. So negative 3 pi over 4 would take us down there. And a negative r value would then take us backwards from quadrant 3 to quadrant 1.
For like navigation, we use polar coordinates. The
Mhm.
zero's like
North.
north, and we go clockwise.
Mm-hmm.
How does that? Are those two completely separate things?
I mean, it's similar. It's just we use a different orientation.
Okay.
But it's the same idea.
Yeah.
It's the same idea. You're going to rotate, and you're going to also have a distance. But for navigation, you just choose a different origin, a different starting point. But it's absolutely similar. So if we want to plot these points in a regular polar grid, the thing that's a little weird is that this is r comma theta. Yet when we write our polar equations, we usually are going to write r as a function of theta when we get to equations, which is a little weird because when we do x comma y, y is the second one which we use as our dependent variable on the first coordinate. Whereas in polar it's backwards. Usually you're putting r in the first position, theta in the second, and usually you're doing r as a function of theta. So with y's and x's, it's y as a function of x, but with thetas and r's, it's r as a function of theta. So it's funny that they do it backwards. So we'll get to that in a minute though. So first off, and it's also, there's no standard on when you look at a point in ordered pair, how do you know if you're in polar or Cartesian? Like they don't tell you. Just because that's a pi, it doesn't mean it's not a regular y coordinate in Cartesian. So you have to sort of decide from the context. So they're telling us here, it would be nice if they put a little p down here to indicate that it's in polar, or an r to indicate that it's in rectangular, but they don't. So 1 comma 2 pi over 3, we're going to go to 2 pi over 3 counterclockwise rotation. We're going to go 1 unit out, so that's going to put us right there. That's that polar point. This one here, we're going to go to 3 pi over 4. So 3 pi over 4 is right along there. But then we're going to go to negative 4, so we're going to come backwards down this line here to negative 4, so that's going to be right there. So this one is in red, and the other one is in blue. Okay? So now if we want to convert these, so our point, let's use a letter to represent these. I'm going to call the blue one P. I'll call the red one Q. So if we want to convert, it's super easy to convert when you're going from polar over to Cartesian. Because we have this equation for x, and we have this equation for y. So if we have those two equations, it's super easy, right? We just plug and chug. So x is going to be r cosine of theta. So r is 1 cosine of 2 pi over 3. Cosine of 2 pi over 3 is -1/2. And if we go to r sine of theta, we have 1 is r sine of 2 pi over 3. Root 3 over 2. So this one happens to be right on the unit circle. And if we want to go to q, same idea. So we're going to do r cosine theta, r sine theta. We look down here. We're going to have r is -4. Let's write this one out in more detail. So -4 multiplied by cosine of 3 pi over 4. And then the y is going to be -4 sine of 3 pi over 4. So cosine of 3 pi over 4 is -√2 over 2. Everyone agree? Cosine 3 pi over -√2 over 2. So -√2 over 2 multiplied by -4. And then this one is going to be -4 multiplied by sine of 3 pi over 4. Sine of 3 pi over 4 is positive √2 over 2. And when we simplify this algebra here,
2√2.
2√2. And that's this point Q down in quadrant 4, positive x, negative y. So the r value can be positive or negative. Normally we're thinking about r as a magnitude, but in polar is the one exception. Now the funny thing is, as soon as you get to Calc 3 and you go to cylindrical, r is now positive. But when you're just doing polar, r can be negative. All right, let's just express these following Cartesian coordinates in terms of polar in at least two different ways. Let's look at this one first. We'll probably just do this one. And this is interesting because if you look at 0, -9, you're down here. You should just be able to look at it and figure out what r comma theta is. So r comma theta, what do you think r is going to be?
-9. Oh, 9.
If we do it in standard form,
9. Yeah.
9, and then theta would be
3 pi over 2.
3 pi over 2. Now, if you wanted to do what Lincoln suggested and say, hey, let's use a -9,
Let's delete pi over 2.
pi over 2, exactly. Yeah, so you could do that. So we'll stop there. Polar's a little squirrely. You can do a bunch of weird things, but it's going to be very useful in the long run, for sure. All right. We have less than 2 weeks left. 3 class periods.
That's right.
Time was not right for Sean Carter.
Crazy, crazy.
Con card